Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today I'm doing the day 19 of the Advent of Code Challenge, or rather, I've already done it. Or rather, even than that, I failed to do it by myself. So I'm going to talk you through the puzzle in both parts, one at a time. I'm going to show you my attempts at solving it, and then I'm going to show you what I wrote instead when I finally gave up doing it myself and took hints and solutions from online. So let's get into it. Day 19, Linen Layout. Today, the historians take you up to the hot springs on Gear Island. Very suspiciously, absolutely nothing goes wrong as they begin their careful search of the vast field of helixes. Could this finally be your chance to visit the onsen next door? Only one way to find out. After a brief conversation with the reception staff at the onsen front desk, you discover that you don't have the right kind of money to pay the admission fee. However, before you can leave, the staff get your attention. Apparently, they've heard how you helped at the hot springs, and they're willing to make a deal. If you can help them arrange their towels, they'll let you in for free. Every towel at this onsen is marked with a pattern of coloured stripes. There are only a few patterns, but for any particular pattern, the staff can get you as many towels with that pattern as you need. Each stripe can be white, W, blue, U, black, B, red, R, or green, G. So a towel with a pattern GGR would have a green stripe, and then a red stripe, in that order. You can't reverse a pattern by flipping a towel upside down, as that would cause the onsen logo to face the wrong way. The official onsen branding expert has produced a list of designs, each a long sequence of stripe colours that they would like to be able to display. You can use any towels you want, but all of the towel stripes must exactly match the desired design. So to display the design RGRGR, you must use two RG towels and then an R towel. An RGR towel and then a GR towel, or even a single massive RGRGR towel, assuming such towel patterns were actually available. To start, collect together all of the available towel patterns and the list of desired designs, your puzzle input. For example, and it gives an example here, possible towels that we have and the possible designs that we need to make. The first line indicates the available towel patterns. In this example, the onsen has unlimited towels with a single red stripe, unlimited towels with a white stripe and then a red stripe, and so on. After the blank line, the remaining lines each describe a design the onsen would like to be able to display. In this example, the first design, BRWRR, indicates that the onsen would like to be able to display a black stripe, a red stripe, a white stripe, and then two red stripes, in that order. Not all designs will be possible with the available towels. In the above example, the designs are possible or impossible as follows. BRWRR can be made with a BR towel, then a WR towel, and then finally an R towel. I'll skip through all these, except to say that UBWU is impossible. In this example, 6 of the 8 designs are possible with the available towel patterns. To get into the onsen as soon as possible, consult your list of towel patterns and desired designs carefully. How many designs are possible? Your puzzle answer was 322. This is because I've already solved it. So I read through this and I felt pretty confident. At first I didn't know what to do, and then I thought, it's actually fairly simple. You just use a recursive function. You take the first character, let's say, see if there's a towel that matches it, and if there is, you check the rest of the string to see if it's also possible. R, does that have a towel? It does, it's got the R towel. W, does that have a towel? No. So then you have to add on the next character. So then it's WR. Is WR possible? Yes, it's here. And then the last character is R possible? Yes. So pretty quickly, you have an algorithm where you just go through the string, appending characters until you find a matching towel pattern. And if you end up with some characters left over, then it's impossible. But also, that doesn't cover everything. And I'd actually already thought of this. So what's a good example here? I can't find a good example, but essentially, if you take, let's say, the character R, it might make the rest of the towel impossible. So let's say we didn't have the towel WR, but the towel RW. Then when we did B and then R, because it should be part of an RW towel, we've made it impossible. We've failed to find a possible solution. So not only do you need to search through and keep clearing your string as you build it up if you find a matching towel, but you then need to be able to backtrack and continue on in case you find that the rest of the string is a failure. So I already had an algorithm in my head for how to be able to do this. Let me take you through my parsing code and then my first attempt at solving the puzzle. So it's pretty simple in terms of the normal setup. There's a unit test that tests that the part A gives the correct result, which would be 6 in this case. I do a from string, which is also fairly simple. It takes the first line or the 0th line, returns if there's no towels found, splits by the comma, maps it to a string. There you go, that's all of the towels collected into a vector. Also checks if the vector is empty. Then it does a similar thing for the designs. So it just goes through all of these lines and collects them together into a vector. So that's even simpler. Then part of my solution, I found that these two variables might come in useful. So I added these later on, as well as the towel counts hash map. Initially, my structure was just towels and designs. That's what I worked with. I've left the others in because I've kept all the functions I wrote as alternate methods, and you can see what I'm trying to do with each of them. Okay, so that's the towel designs parsed, pretty simple stuff. The next was the is possible function. So my part A, I wrote a very simple loop. It simply did designs, and then you iterate through the designs, self.designs, filter it if it's possible with the isPossible function, which is now called isPossible alt3, and then count how many match the filter, how many pass through the filter, meaning that they are possible. So the actual part A is very simple as soon as you've got an isPossible function, which is what I was trying to write. So I started writing the isPossible function. Now the first thing that I did was check if I knew that I'd need a recursive function. So I started out without this cache, and I just wanted the isPossible function. What it would do is check if the string being passed in is already in the towels hash set. Did I store it as a hash set or a vector? Oh, I stored it as a hash set for quicker lookup. So it collected it. It checked if the remaining design was in the towels. If it was, returned true. This string is possible. From then on, it started going through all of the different, well, it started out by going for index in 0 up to remaining design.length. That was my initial algorithm. And I'll tell you why I took that out once I get through this a little bit further. So I wrote the check string as indexing 0 up to the index. So if you want a string of length 1, you do 0 up to 1. And because a range is exclusive, meaning 0.1 only contains the value 0, it would just give me the 0th entry. So it just pulls out the 0th character of remaining design. That's my check string. The idea being that I can then, if the index goes up, I get a 2-length string and then a 3-length string. So if we don't find a matching character, we can just keep building up that string. The leftover design is the remaining design from that character onwards. So if you're checking a string of length 1, the leftover string that you need to check is from that index onwards, right? So that would be if check string is possible, then I need to check if the remaining string is also possible to determine whether the whole string is possible. So first, does my towels hash set contain that check string, right? The 1, 2, or 3 characters, or however many that I've currently got. If so, then also check if the rest of the string is possible, right? So pass in leftover design. Now at this point, I didn't have the cache. I'll get to that in a moment. So this would have just been deleted. If both contained and is possible are true, then return true. Otherwise, We get to the end of this for loop, we return false. So that was pretty simple, and it worked on the test cases immediately. Then I took the input.text and I thought, yeah, we'll see how it goes. And it took absolutely ages. It took so long, I guess because it was doing forwards and backtracking and so on. So unfortunately, that didn't work. I started trying to think about how to speed it up. And the first thing that occurred to me very quickly was that I need to cache it. I need to produce a cache that contains all of the possible strings as I find them out. Because then if I come across those strings again, I already know it's possible. So let's say that I'm checking the string UBU and I can possibly use U and BU, right? So U is possible, so then I want to go on to B. Is B possible? No, we don't have a single tal that does that. Is UBU possible? Is BU possible? Yes, we have a tal for that. Therefore, I want to store in my cache that UBU is possible. We've just found out it's possible. From then on, any string we get, like a arg UBU, we already know that UBU is possible because it's in the cache. We don't need to calculate it again from the single tals U and BU. We know that UBU is possible. So that I felt made sense. As I was iterating through, I would keep adding things into the cache. So my code to do that, let me undo until I get the cache back. I decided to pass the string that I had calculated so far into the function, so that whenever I find a possible towel entry, I can add it onto the end of the cache and I can insert the whole thing into my overall cache. And this is where the I think I do a self.towels.insert, right? So that's just saying I have a list of possible towels, right? So if I add another possible combination of towels, I might as well just count that as a new towel. So I insert it into my towels hash set. And as soon as I do that, I had to make the function mutable. It had to be able to change its own hash set of towels in order to cache the possibilities as I calculate them. So that's how I did it. Within the is possible, that means that we found a valid combination. I did originally do it in self.towels.contains as well, but I decided that it wasn't worth it because it would be inserted in this code block, so it was unnecessary. So you can ignore all of these commented lines. You can also see a lot of print lines from where I was trying to figure out why my function was slow or wrong. In any case, we get down to here and we figure out that the string so far is the cache plus the check string that I've just calculated. So now that whole string is possible. But also, I've just done is possible on the leftover string, which means that the leftover string is also possible. So then I add that to the hash. I've just realized that one thing I didn't do here was add the check string plus the leftover design to the cache, which would have made a lot of sense. In any case, again, that worked. It passed the test cases. I don't know if it sped it up because when I read it on the real thing, it just took forever. I believe that what happens here is that it keeps recursing, right? And it only adds entries once it gets to the end of the string and realizes the last few letters are possible. So for this example string at the top, it starts at the left, it works its way all the way through until it gets to the end. Then it says, let's say UBR is possible. So then it figures out UBR is possible, and then it adds that to the cache. And then it has to work all its way back through the string. And by putting in print lines, I realized while running the real input case that I never got to that point. I never got to the end of the first string. It was taking too long to calculate even one string to cache entries from it. So that's when I tried to think about ways to speed this up. So one thought that I had was, instead of calculating one character inputs, if you look at the input list here, they're mostly 3, 4. I'm not sure there's a single character of length 1. So why am I calculating one by one? Actually, I just saw B alone for a moment there. Yeah, there it is. Which just goes to show that this optimization did absolutely nothing. But essentially what it did was go through my current list of towels. It took their it took their lengths, and then it iterated over that array. So if I don't have a 4-length towel, there is no point in checking a 4-length string. Just go straight to the 5-length towel. That was my idea, so I started iterating in the towel lengths. I also decided that if I sorted it smallest to largest and then checked the largest first, that might be more likely to get to the end of the string and start caching entries faster. So I did that. Towel lengths. I also realized that if there's only so many characters of the remaining design left, there's no point checking for more characters than that. Hence this filter, only include the towel length if it's less than the remaining design string length. And that's my entire string. And as I said, it works, but it's way too slow. I needed a better way. So I started writing the isPossible alt. And this is where it gets somewhat frustrating, because I think this algorithm is incredibly close to what the correct solution is, or at least a working solution in a reasonable amount of time. So what I do here is I find all the towels available where the design starts with that towel. So if I have the string UBU or UBU, and then I have the towels U and UB available, and G, then I iterate over this list, and I see that my design does start with U, so U should be kept. My string does start with UB, so UB should be kept. But G, it doesn't start with G, so I can filter out G, right? Now that's my list of designs to check through. Then I iterate over, and then I went through a similar process. I did it without caching and then added caching in. I don't think I need to go over this too much. Something that I started doing was using an insert cache function, because I wanted to calculate the max towel length and a hash set of the towel lengths that I have. So instead of just inserting directly into the towels hash set, I created insert cache, which inserted into the towels hash set and updated the max towel length and the towel lengths hash set. By doing that, I was hoping to avoid complicating the code, even though it would take the same amount of time writing it out manually. So then I started doing the recursive function again, except it only did the designs that were possible. In the end, I decided that this was roughly the same as the previous function anyway, because I was only checking the possible towel lengths in the previous function, and in this I was only checking the possible towels. So in the end, it was pretty much the same thing and didn't get anywhere. So then I went on to isPossible alt 2. Now on this one, I started trying to make the string into a stack of characters so that I'd go right to left, and I'd pop them off, and for each one I'd check if there's a valid towel, and if there is, I would check or the left of the string, or rather the remaining stack, because that's what's left. Unfortunately, it's not exhaustive, because if I find, let's get a 3-letter combination that shows it. If I, let's say I have RBR, or BBR, there we go, and I have the towel R, and I have the towel, this is a terrible example because it doesn't work. Okay, this is a good example. So I can pop off the B character, I check that it has a valid towel that matches it, so I clear the check string that I'm currently building up. So this is my candidate string that I'm building to check. Then I'm left with BR. R doesn't have a candidate. BR doesn't have a candidate. So I need to backtrack. I need to go back to BRB and then check RB instead. And I couldn't figure out a neat way to do the backtracking. And this is the point on my third possible solution where I decided to take a hint. I didn't want to take a solution. I decided to take a hint. Someone on the Advent of Code subreddit was asking for help, and they said they'd tried a few things, including regex. So I decided to write a solution that used regex. This turned out to be really simple. Basically, all that you do is take your possible towel patterns, combine them with a pipe symbol in between them, meaning or. So if I have the possible towel solutions R and B, then my my regex would become R or B. Then I need to do some extra regex stuff around it, as in the hat means the start of the string, dollar means the end of the string, and by putting a plus in there, it means this group 0 to as many times as you can fit it. So by doing that, it would only match strings that can be made up with some combination of this pipe-separated list. And that worked very quickly, and I felt relieved. I wasn't surprised I hadn't thought of it, but thought, oh, that's useful to know for the future. And so I took the answer from this and I went on to part 2. So let's take a read through part 2, and you might be able to see why the regex doesn't help. Part 2. The staff don't really like some of the towel arrangements you came up with. To avoid an endless cycle of towel rearrangement, maybe you should just give them every possible option. Here are all of the different ways the above examples designs can be made. BRWRR can be made in 2 different ways. BRWRR or BRWRR. BGGR can only be made in 1 way. GBBR can be made in 4 different ways. RRBGBR can be made in 6 different ways. The impossible ones are still impossible. Adding up all of the ways the towels in this example could be arranged into the desired designs yields 16. They'll let you into the onsen as soon as you have the list. What do you get if you add up the number of different ways you could make each design? Here you go, here is the solution. So let me talk you through what I tried to do, and then my process of giving up and copying other people's solutions. So I wrote a count possibilities function. In my part B function, all I do is take the designs, I map it to the possibilities for each design, and I sum it up, where if it's impossible, then the number of possibilities is 0. So that's pretty simple. Count possibilities, I tried to use the regex again. And for some reason, I couldn't get it to match more than once. It wouldn't try every possibility of a regex. As soon as it had a match, it stopped calculating. Because it's made for searching along a string to find a particular pattern. It's not made for searching the same string and finding different possibilities for the pattern. So what I ended up with is 1 possibility if the string was possible, and 0 possibilities if it wasn't possible, which didn't give me the right answer. I needed to find something else. And that is where I sat and thought. I thought about all of the is possible functions I'd done and how I could adapt them and how they were too slow anyway. And I decided I'd spent enough time on it and to try and look for help online. That is where I found one possible solution that came from a subreddit comment on the mega thread for possible solutions for this page. So I took the code, and again, just as last time I took a solution, it was incredibly simple. This was the linear algebra solution, which was, I think, day 13. The link to this solution will be in the description of the video, so you can go straight to the comment and see it for yourself. So essentially, sorry, this is stolen 2. Stolen.py. Again, much, much simpler than what I've written. So all I've done is modify it slightly. Instead of taking things from the input, they're taking it from test.txt, saved to disk. The max towel size is the same. And what they did, I just did not understand. So I took it and I copied it into a function, rewrote it in Rust so that it would match the rest of my code. And then I found it worked essentially immediately. So I could vaguely work out what it was doing. It had a dictionary of counts. It would take some substring, max of 0 and the index it's checking minus the maximum towel size, and then it did some reverse j to I to substring the pattern, and I didn't get what was going on. I didn't understand how this was a possible solution and why it worked better than my solution, where I tried to do something pretty similar. So because I didn't really understand it, no fault of this person, I'm sure it's a clever solution, I just don't understand it myself. I went and found a YouTube video, and I don't remember the name of the channel that did it. I will link it at the top and in the description if you want to go and check it out. The person that I watched is a speed solver. They're much better at advent of code than me. They solved this immediately without any effort, apparently, and then explained their solution once they'd got their leaderboard position. So thank you to that person for explaining how it worked. It ended up being very close to what I was trying to do, and I think I just did the caching incorrectly, and I didn't think to use the caching to store the result count, which I absolutely could have. So this is not the entire solution, this is just the part of the YouTube video, part of the code that I copied from the YouTube video that was relevant to what I was trying to do. So the solve function, it is again using a cache, and it has a global cache, and it basically says if it's not in a cache, figure out what it is. If the length is 0, then there is one possibility to make it. Otherwise, there's 0 ways to do it to begin with. Then, for the possibility in the towels that I have available, add one, or rather, add as many entries as there are available. So add the result of the solve function. So it is again doing a recursive function call. It is passing the string from the end of the current towel onwards, which is what I did in my alt is possible function. And yet my is possible function is very, very slow, and this worked instantly. So what I'm learning from this is that I don't understand how to do dynamic programming very well. Although my instincts went to do caching, I didn't do it correctly. What I'm going to be doing is, after advent of code, I'm going to be taking some LeetCode problems and trying to practice doing that. It's called dynamic programming because it is a combination of a recursive function call. This is solve, the recursive function call, and memoization, which is where once you've calculated the result of an expensive operation once, you save it so that you don't need to redo it. And that's this caching. If it's not in cache, then calculate it. Otherwise, just return the cache entry. So the result of the solve function is all the possible ways that the substring could be made up. So it recurses through until it gets to the end of the string, and then it builds up the count of possibilities all the way back up to the top. And the whole while it's saving for a particular substring how many possible ways there are to make it. Then it returns that entire cache, it returns the entry of the cache for the full design that is being solved. So I copied this, I did my count possibilities Alt-2, and it's pretty much the same code, right? If the design is empty, if the length is 0, return 1. If it's in the cache, I tend to prefer, instead of if I can get away with it, I can't always, but rather instead of doing if self.towelCounts, if not self.towelCounts.contains, let's say, which would be equivalent, contains key whatever, then wrap the rest of the function in it. I prefer to return early if I know that the result is not possible. So in this case, I would have said if s in cache, return cache s. Otherwise, do the rest. That would have been my version of this, which I feel is more reasonable. In fact, we don't even need this else. We can just tab this back in. Right, so then it's more inline, it's more readable in my view. But I'm not critiquing the code written by a speed solver. They definitely wrote it quickly and they definitely got it right. They're not trying to write neat code. And they may disagree with me about the neatness of the solution anyway. Back to my solution, I get the result is 0. I clone the list of possible towels that I have, and that's so that I can do this mutable function call. Otherwise, the Rust borrow checker gets in the way. It says, hey, you're borrowing the towels hash set immutably. You can't also borrow self mutably at the same time. That's not allowed. So if I clone the towels, then I'm allowed access to it. And most likely what happens is that the Rust compiler realizes that I'm never modifying this towels, I might as well just leave it where it is, which means that there's no extra time or computation needed for this if it's been optimized. So doing this is perfectly reasonable. From then on, for towel and towels, if the design starts with the towel, continue. Otherwise, count the possibilities. Now, that's not exactly the same as what they've done, but it has the same effect. And this gave me my final answer, one that I'm actually happy with. I feel like I understand how the solution was come to, and I understand that I need to practice dynamic programming in order to solve this kind of problem much more quickly. So again, thank you to the author of stolen.py and to the author of stolen2.py. Both the links for both of these will be in the description, so you can go and take a look at the originals. That is the end of day 19. Thank you for watching, and I'll see you for day 20.